Thank you. My pleasure. So I'll be presenting on behalf of my team, which includes now Dr. Reza Nasuri, who was a former PhD student of both Dr. Matamoros and myself. And we have been working on the reliability of high mass illumination poles for about 4 years. So this will be actually a brief summary of the work that we have done so far. So the motivation for our work is that most steel structures, they have to go under a galvanizing process because that creates a coating layer that protects the structures from corrosion. And it is actually a very effective method to protect steel structures from corrosion. However, it has some flaws because it has been detected that after this galvanizing process, they have detected small weld-toe cracks. And these weld-toe cracks developed during galvanizing. Now, if these small cracks go undetected because they are exposed to fatigue loading from winds while they're in service, they can actually propagate and the poles can fail and cause a catastrophic failure that can even cause some loss of human lives. So it's very important that we try to minimize the formation of these cracks. So we're trying through our study to provide some guidance to engineers, galvanizers, and fabricators on how to minimize the likelihood of crack initiation during the fabrication process of high mass illumination poles. And our methodology has consistent first on developing a reliable finite element model that can capture the high stress demand spots induced during the hot dip galvanizing. And actually, it is important to develop a model because there's very limited that we can track experimentally because the temperatures of the hot dip sink bath, they are in the order of 800 Fahrenheit. So strain gauges actually melt. So it's very hard to predict, to track the behavior of the structure during galvanizing. So the models have become a great tool to study these structures. Then we, through this models, we try to identify the critical stages of the galvanizing process and the potential crack initiation sites. And then finally, we conduct the parametric study to see that if we perform small changes in the geometry and the galvanizing process, we can contribute to minimize this cracking phenomenon that has been observed in high mass illumination poles. So first, let's go over our finite element model. This is the geometry that we have used. Typically, high mass illumination pole, it's composed of a pole and a base. And you have base at both sides. These are typical dimensions. There are many details when it comes to the connection between the base and the pole. They vary by state. We have modeled different of them. In here, I'll be presenting results for the Wyoming detail. And what the Wyoming detail has, it's a full penetration weld between the pole and the base, and then a backing ring. And this backing ring actually was introduced to improve the fatigue performance, but actually didn't consider its impact on crack formation. And so through the study, we also try to capture the impact of the backing ring on the crack formation phenomena during galvanizing. So a typical galvanizing process consists of 4 steps. So first, you dip your pole, typically at an angle, and then you leave it there for some time to make sure the sink attaches to the pole and the base. Then you extract it, and then you finally let it cool down. So this is the process that we are modeling through our finite element simulation, and for that we do it through a coupled temperature displacement analysis because we are interested in both the temperatures and also the mechanical response of the structure. So these are some results of our simulation, which we're trying to capture the bath process. So we created some user routines in Abacus to be able to develop, to mimic this galvanizing. And here you can see as you submerge the high mass illumination pole through the sink bath, the temperature changes quite rapidly, and then you extract it, and then the structure starts cooling down, as you can see here. So we were able to calibrate our model with some experimental results that were available for early stages for the simulation. There were some thermocouples there that we were able to have good agreement with them. And then let's look at what would be the critical stages of this galvanizing process. So here you'll see the stress results at a bend of the pole to the 4 different stages, which are deepening, dwelling, extraction, and cooling. So you can see during deepen, we have this huge thermal spike. And then during dwelling, the stresses somehow level off. There's not much variation, but then during extraction, there's another increase in stresses, and then this level up during cooling. But after this process, there are some residual stresses that are left on the structure. It is important to know that we use the thermomechanical properties, and the mechanical properties are temperature dependent. So the yield stress, it's lower and changes with the temperature. Then from our simulations, we were able to extract the stresses along a path of the pole, and we considered different distances from the base plate. And here you see radial stresses that denote, that show the tensile stresses and the compressive stresses through this path. So here it's at 5 millimeters and at 10 millimeters. As you get closer to the base plate, the stresses are higher. And but an important observation is that from our models, we were able to capture the location of potential weld toe cracks, because as you can see, the spikes of the stresses, they are always at the bend, particularly bends 3 and 10. Another measure that we used to capture this potential locations of cracks was the equivalent plastic strain. And I particularly like this, this measure because the stresses are time dependent, so they vary up and down during the simulation, but the equivalent plastic strain keeps accumulating. So it's a measure of the deformation gone by the material throughout the simulation. So you can see here there are 2 spikes. One, it's when you dip the high mass illumination pole, and then the other time is when you extract it from the bath. And the maximum plastic strains are observed at bends 3 and 10, which is in agreement with what has been observed during fabrication. Then we did a parametric study to see what would be the effects of geometry on this crack formation phenomena. So we first kept the pole thickness constant, and we changed the base plate thickness. So you see here that we consider different base thickness. So that will give you different VP ratios, as we call them. And here you can see the effect of the VP ratios. So you can see that the largest spikes are for higher values of VP ratio. So when you have a VP ratio of 11, you have this purple line, which indicates the highest spikes. And then for lower values of VP, the stress demands are lower. And this is just a zoom to indicate that same observation that PQ, which is the equivalent plastic strain, increases with the VP ratio. Then we just compared the effect of the pole thickness by keeping the base constant. And from here, we can observe that if the pole thickness is lower, then the stress demands actually are going to be higher. In the interest of time, let me move on to the next slide, which shows similar information in which a lower thickness corresponds to higher stress demands during galvanizing. Then we also study the effect of the curve of the shape of the pole. So here you see we consider 8-sided pole, 12-sided pole, and a round pole. And we repeated the galvanizing simulations. And as you can see, the round poles actually are the ones that require, that actually have less stress demands during the simulation. And then the 12 and 8-sided poles, they have similar demands. So actually, it seems that curved or round poles actually would contribute to lower down this crack formation phenomena. Then future and current work, right now under Tran-SET support, we're actually also trying to include the effect of welding, because we realize that the manufacturing of HMIPs is actually consists of different manufacturing steps. So you first have to do some cold working on the steel pole, then you have to weld the base plate to the pole, and then you go through hot dip galvanizing. So under this new grant, we incorporated the effects of welding. And so we had this metal part already simulated, and we added this part to the simulation, both welding and cooling. And in here, I showed the stresses and the equivalent plastic strains through a path. And the horizontal line indicates the maximum stresses and plastic strains that we were obtaining just during the galvanizing phenomena, and then what would be the resulting stresses and strains once you have welding plus galvanizing. And as you can see, there's actually some higher values due to this by introducing the welding to the simulation. So some conclusions, we saw that the results revealed maximum strain and stress demand at the deepening stage. That's where we saw that thermal shock. It was the highest when the HMIP was partially submerged. Then through the parametric study, we saw that poles with the same pole thickness and smaller ratios of pole to base plate thickness correspond to lower stress and strain demands at critical locations. And then in models with the same plate thickness, stress and strain demands were determined higher for thinner poles than for thicker pole shafts. Also, stress and strain demands were found to be lower for poles with circular shapes than for multi-sided poles. And finally, we can see that the stresses and strains generated at welding can also be contributing to the weld toe crack formation. So these are the reference, and yeah, please let me know if you have any questions.